Assalamu alaikum, dear students. I hope you are fine and doing well in your studies, and I wish so. Well, this time we are meeting again. This is the lecture number 3rd on this linear differential equations with constant coefficients. It is continuing from lecture number 2. Whosoever you goes to lecture number 3 directly, but I suggest to you should first go to lecture number 1, lecture number 2, and then lecture number 3. Before going ahead, I would share with you. I could finish this linear solution of linear differential equations with constant coefficients within a lecture of 4 within 4 lectures only. But the fact is that I want to give you something informative. I would like to share with you something informative, that when the roots of this auxiliary equation are all real and different, what happens? When roots are equal, what happens? When some roots are complex, what happens? Because in the solution we sometimes remember this working rule only. In maximum books or maximum teaching this aids, you get only the rule. It is when finally you have to remember the rule, but first you should know where from the rule comes. Actually, I have already told you it is very important for the students who are pursuing the 5-year integrated courses or the honors in mathematics or the BSc in mathematics. They must know where the proof comes, and finally you will remember the procedure of the solution that I will also share with you very nicely, inshallah, God willing. I will be sharing with a suitable this method, how you remember the solution, how you do quickly solve the linear differential equation of any order. Okay, well, last time if you go to lecture number 2nd, what we did there, we just focused on this auxiliary equation. What is an auxiliary equation? We will again now write the how to solve. It is actually, I shall start now solution of how to solve. This is how to solve linear differential equation with constant coefficients. In other ways, you can say it is the method of solution. I will again consider, as we did previously, consider the linear differential equation with constant coefficients, say of nth order I am considering, because order can be any. This I am considering nth order. This, as usual, I will take dny dxn. This is the constant here, some constant p1, then dn minus 1y dxn minus 1, then plus p2 n minus 2 derivative of y with respect to x, then so on. You write p n minus 1. This is dy by dx. This is p and y, and right side is 0. You know what is the symbolic representation of this? Symbolic representation of this is this equation is. That is why I am telling you to go to lecture number 2. There you will get the symbolic representation. I can write now it in short form. I can write this is this equation: dn plus p1 dn minus 1 plus p2 dn minus 2 plus dash dash so on to pn minus 1. It is d, then plus pn into y is equal to 0. This is the equation in D, nth degree equation, nth equation in D, nth polynomial in D. I will write it f of d into y is equal to 0. This is your now short form of this given equation, as you do. In case of you have here x, you will write f of dy is equal to x, and there I have told you that we have two parts of the solution in case right side is x. One is u, known as complementary function. Second is v, known as integrating this particular integral, particular integral v. Okay, when this is x, in that case you need the particular integral. When it is 0, you have the solution, only one part of the solution, that is complementary function. This you know. Then you know, for auxiliary first setup, when we write the given differential equation in the symbolic form, first method setup is write the differential equation in the symbolic form. It is not necessary you will have always dy by x. You can have dr by d theta. In that case, your capital D will be here. In this case, I am taking d as d upon dx operator. But instead of this dy by dx, I may have dr by d theta. My capital D will be there, d by d theta, so on. Well, in this case, you have the auxiliary equation. Auxiliary, I will write here full form. It is this short form we write AE. Auxiliary equation is it is f of d is equal to 0. Okay, f of d is equal to 0. This means we have to solve. When you write f of d is equal to 0, what does this mean? This means you have dn plus p1 dn minus 1 plus p2 dn minus 2 plus pn minus 1d plus pn is equal to 0. This is equation number second, suppose. And we solve this equation number second, where we treat d as some algebraic quantity. We have it will give us n roots. I will again write this equation second. If it is not visible, it is at the bottom. It is dn plus p1 d n minus 1 plus p2 d n minus 2, so on. It is your p n minus 1 d plus pn is equal to 0. This is second equation. Well, it is a nth degree in d. Treating d some algebraic quantity. That is why in some books you will see that this d is replaced by m. Then the auxiliary equation becomes m raised power n plus p1 m raised power n minus 1, so on. And in some maximum times we can directly solve it for d. Treating d some algebraic quantity, equation number second is nth degree equation in d, and will have n roots in d. In other words, it has n values, and that satisfy in this equation by the fundamental theorem of algebra. It is a nth degree in d. There are n values, n roots in this. Now these n roots are of different nature. We have to investigate here. When the roots are all real and different, this is one case. When roots are real but some of them may be equal, this is second case. When roots are a repeated case comes equal, second case repeated also. When roots are complex, and you know that complex roots occur in conjugate pairs. We will discuss main three things here. Otherwise you can directly remember the formulae, how to find out the solution when roots are all different, how to find out the solution when roots are when some of the roots are repeated, how to find out the solution when roots are complex. Finally you have to remember the direct, but I am just giving you the informative lecture how it comes. Okay, you see, I will consider here different cases. Okay, I will take the case number first. You have come to know that it will have now n values in D, n roots. I will consider here case first. Case first I will write, it will be when all roots of equation second are real and different. When all roots are real and different, say alpha 1, alpha 2, alpha 3, alpha 4, alpha n be n real and different roots of second equation. Now I will concentrate on one of the roots, different roots. Then I will write the other solution similarly. There is no need of taking each and every root. I will take if when alpha 1 is the root of equation first, when alpha 1 is a root of equation number second, when alpha 1 is the root of equation number second, what happens? When alpha 1 is a root of equation this, it will also be the root of first, because that involves the f of d into y. Alpha 1 is the root of equation second. This implies that d minus alpha 1 is one factor of second. This is by factor theorem. I am giving you the information also. It is by factor theorem. You might have done this in your theory of equations. When d is equal to alpha is a root, d minus alpha will be the alpha 1 is factor. That means I can write down the given equation first. This implies I can write down f of dy can be written as, it is equal to say phi of d minus alpha 1 into y. Very important step. Clear? Because the fact is, when we divide the f of d, I will give you the just this your recapitulate your this theorem, factor theorem. It is when d minus alpha becomes the factor of f of d, it means it will divide this f of d exactly. When you divide f of d exactly, you will get a quotient. It is this phi of d. What will be? It is degree. It is again a polynomial. It is degree will now get reduced by one factor, by d. Why I write d minus alpha 1? Because d is the root of this equation. It is in d. If it would be in x, then it will be x minus alpha 1 is a factor. That you know. Where I will write, where phi of d is polynomial. It is a polynomial of degree n minus 1 in d, because from f of d you took one factor of degree 1. The remaining quotient, remainder will be here 0 because it divides it exactly. The remaining quotient is here phi of d. It is degree will be now n minus 1. Okay. Now I will state here a very important this information, that is this. Now the fact is here, any solution of this part, d minus alpha 1 into y is equal to 0. If you solve this, d minus alpha y is equal to 1, if you solve this, any solution of this is also the solution of f of dy is equal to 0. F of dy is our original equation, first equation, because when you get the solution of this, that means there are some values which make it 0. Solution of this, it is the part of this f of d, so it will also satisfy this, because alpha 1 is also the root of this f of d. Okay, so let us solve this. Any solution of this is also the solution of f of dy is equal to 0, because we have obtained this d minus alpha 1 y from this first. Well, what is this now? This implies d of dx, give the value of d, alpha 1 y is equal to 0. This is dy by dx is equal to alpha 1 y. This is alpha 1 y. Variable is separable, I will write. This is equal to dy by y is alpha 1 dx. So you have variables got separated. Variable is separated. So when you integrate this variable separable method, this will be what? Integral of 1 by y dy is integral of alpha 1 dx. I could write here c1, no problem, you can write, or you can I want to write it a solution in the form of y is equal to y1, the first theorem, y is equal to y1, y is equal to y2, y is equal to y3, so that you can generalize that theorem when y is equal to y1, y, because it is the one particular solution of this. You are not getting each and every solution, it is a particular solution. In the first theorem we stated if y is equal to y1, y is equal to y2, so so on to y is equal to yn is the solution of, now I will write f of dy is equal to 0, then complete general solution is y is equal to c1 e raised power alpha 1x plus c2 e raised power alpha. I could also write here c1, no problem, then I can write the linear combination of the solution that gives you the solution in that way also. This is your log y, this is alpha 1x, this I can write log y is equal to log of e raised power alpha 1x. ठीक, this means you get one solution y is equal to e raised power alpha 1x. No problem. If you write here plus c, then that c1 you will choose as log c, then this will be log m plus log n. Here it will be log of c1 e raised power alpha 1x. Here you can have the solution y is equal to c1 e raised power alpha 1x. And in second case you will have solution y is equal to c2 e raised power alpha 2x. Then you have y is equal to c3 e raised power alpha 3x, so on. I have here just this skipped the constant of integration that will not be, that we will get in the by the first theorem. Now I got this solution when y is equal to, when we took the 1 root d is equal to alpha. It is one solution, particular solution is y is equal to e raised power alpha 1 x. So I will write similarly when d is equal to alpha 2 is root or solution of second, we will get y is equal to e raised power alpha 2x, and proceeding this way, the solutions of equation first are I should use here, this is, we are taking this alpha 2 of first. The solutions of equation first are y is equal to, one is e raised power alpha 1x, y is equal to e raised power alpha 2x, y is equal to e raised power alpha 3x, that is so on, y is equal to e raised power alpha nx. Now in first lecture, where we said if y is equal to y1, y is equal to y2, y is equal to y3, so on to y is equal to yn, or n linearly independent solutions of f of dy is equal to 0, then the complete general solution is, we introduce now arbitrarily constants. Then the complete solution of equation number 1 is given by what? It is y is equal to c1 e raised power alpha 1x plus c2 e raised power alpha 2x plus c3 e raised power alpha 3x plus so on to cn e raised power alpha nx. Well, you have where alpha 1 comma alpha 2 alpha 3 alpha n or n arbitrarily constants. I have already told you again and again, these constants are an arbitrarily constant, but they are also linearly independent. If they become dependent, then you can sometimes reduce 2 into 1, 3 constants into 1, but that is not the case. They are linearly independent constants. Now you have, in short case, if the auxiliary equation has the solution alpha 1, alpha 2, alpha 3, when it is of degree third, alpha 1, alpha 2, alpha 3, that means it will involve 3 arbitrarily constants, c1, c2, c3. You will write the solution y is equal to c1 e raised power alpha 1x, c2 e raised power alpha 2x, c3 e raised power alpha 3x. When it is of degree n, you have to write down n constants, and similarly you will have n roots. It is the solution. Now there is case second. You may put a question. If our roots are real, but some are repeated, how we proceed? I will also tell you, if we proceed this way, we will get some contradiction. We have not to proceed this way. You may write, if roots are say alpha comma alpha 2 alpha 3, that means if we take two roots we are taking repeated. Naturally you would write according to this formula, c1 e raised power alpha x, then plus c2 e raised power again alpha x, because 2 are, then you will proceed this way. But we will see that there we get something that contradicts. So we have not to follow this procedure when the roots are repeated. Sometimes 2 repeated, 3 repeated. I will give you when all roots are repeated, how we proceed. Don't worry. Let us go to case number second. This is case second. We have now case second. This is case second. When roots of auxiliary equation are real, but some are repeated. Some are repeated. Let me take the repeated case, say 2 are repeated, then I will extend that if 3 are repeated, 4 are repeated, or are repeated. Let us assume, suppose roots of auxiliary equation be alpha comma alpha, then alpha 3, then alpha 4, alpha 5, alpha n. That means I take these two, I take 2 repeated here. when two are repeated. Then you have 1, 2, 3. Okay, then you are n roots. 2 repeated. Now let us see what happens if we proceed the previous case first. I will put a question here. Can we proceed as in case first? Can we proceed in that way? We will get something contradiction. When we have to prove that this method fails, this does not suit, we first assume, let the method is correct, then we get something that contradicts us, we then assume no, it is not possible. If possible, let solution of first in case number second. We are case number second is this, roots alpha, alpha, alpha 3, alpha 4, alpha 5, alpha n. We suppose if it is possible, let solution of if possible, let solution of first in case second, solution of first be this is actually second FD y, I have named it. Solution of the equation be y is equal to, actually general solution, no problem, it is general solution. Solution of first be y is equal to, it is c1 e raised power alpha x, then plus c2 e raised power alpha x, because you are getting instead of alpha 1 alpha 2 you have alpha 1 this, alpha 2 is this. Then you will write alpha 3 e raised power alpha 3x plus alpha plus c4, it is c1 c2 c3, it is c3 now, c3, this is a constant c4 e raised power alpha 4x, then cn e raised power alpha n x. Now what happens? You see what happens here. You can write y is equal to c1 plus c2 e raised power alpha x, then plus c3 e raised power alpha 3x plus c4 e raised power alpha 4x, so on to plus cn e raised power alpha nx. What happens? This is c1 plus c2, this c1 plus c2, this is constant plus constant, it reduces to single constant, these are not two now. This is y is equal to, it is c e raised power alpha x plus c3 e raised power alpha 3x plus c4 e raised power alpha 4x plus so on to plus cn e raised power alpha nx. Now here what you observe? You observe that two constants have merged into one constant. So this equation you will not say will have n different arbitrarily constants. The constants involved here are only n minus 1 because two have merged into one. So this means, this implies solution contains solution contains n minus 1 arbitrarily constants, which is a contradiction, which contradicts the theorem that solution should contain n arbitrarily independent constants. So it is a contradiction. We will not accept it. It is not a general solution. So it is not general solution. It is not general solution. We want general solution. We want, what is general solution? General solution is when you have the number of constants, independent constants, equal to the order of the linear differential equation. What is the order of the linear differential equation? That should be the number of constants. But here our linear differential equation is of order n, so it should have n linearly independent constants. But if we proceed in repeated case, the previous method that we did for roots when they are all real and different, if we proceed that case, we get a contradiction. So we are not allowed to proceed that case. So we will give you the method that you will remember for writing down the solution in case the auxiliary equation has repeated roots. You see how we proceed. So we have here posed a question, can we go this way? The answer is no. So it is not a general solution. So it is a contradiction. So we proceed this way. Now how we proceed? We proceed this way. We know for the different roots, say that is alpha 3, alpha 4, alpha 5, the corresponding part of the solution will be say C3 e raised power alpha 3x plus C4 e raised power alpha 4x. We have nothing to do that. That involves the corresponding part involves that solution. Now what we do is we take the repeated roots. Now take repeated roots. How many you took repeated? Alpha, alpha. When you take repeated roots, that means one factor is d minus alpha, second is d minus alpha. So this means by factor theorem, again by factor theorem, you can write first equation, which is f dy. You can write this is now, say it is d minus alpha square, because it is repeated 2 times. So there will be 2 factors, d minus alpha square, say psi of dy. Or you can write this as psi of d minus alpha square y. Okay, here also we write any solution of d minus alpha square y is equal to 0 is also the solution of what? F of dy is equal to 0, because this is a factor of this. It is by factor theorem. Any solution of this part is also the solution of the given equation. So we solve this. Let us solve this separately. We will come to know what will be the roots, what will be the part of the complementary function. It is a part. For the other part, we know there are all roots real and different, but some of the roots are repeated. So we take the repeated case here. So we solve this. How we solve it? You see how we solve it. I will replace here. Let us put here d minus alpha into y is equal to z. I have written here any solution of this is also the solution of this. I will put here d minus alpha into y is equal to z. What happens? This means you will get d minus alpha z is equal to 0, because this is 2 times d minus alpha y. One part d minus alpha y I put z, so it is d minus alpha z. Why so? You have done previously. This means your dz by dx is equal to alpha z. This gives you dz by z is alpha dx. Okay, so variables are separated. Variables got separated here. I can write the solution here. This is log of z is equal to alpha x. Okay, I can write log z is equal to, right here constant, say c1 I will write. This is log of e raised power alpha x plus c1. This is z is equal to, this goes e raised power alpha x plus c1. This is z is equal to e raised power alpha x into e raised power c1. So you get z is equal to c e raised power alpha x. Okay, you have got the solution of value of z. Now what is your this part? Take this part here. You have d minus alpha y is z. How you proceed? This gives you dy by dx minus alpha y is equal to z. The value of z is there. You can put the value of z here. Z is c e raised power alpha x. Now you have to solve this equation. Now we have to solve this. How we solve it? This is dy by dx minus alpha y is equal to c e raised power alpha x. It directly takes the form dy by dx plus py is equal to q. That is linear differential equation of first order. How you write their integrating factor? This is function of x, function of x. You have here y. This can be constant or function of x. Well, this is your yes. This is your integrating factor. You write here it is e raised power integral of p dx. What is here integrating factor? Integrating factor will be here e raised power integral of minus alpha dx. This is integrating factor is e raised power minus alpha x. You remember that solution? How you write solution? Y into integrating factor, because dependent variable is y. It is y into integrating factor integral of q into integrating factor plus some constant c1. Well, this is your y. What is integrating factor? E raised power minus alpha x is equal to, what is your q? Your q is this c e raised power alpha x, c e raised power alpha x. Then integrating factor is this e raised power minus alpha x dx plus c1. So it is y e raised power minus alpha x is equal to, this is c integral of e raised power, it is 0 dx plus c1. This is y e raised power minus alpha x is, this is c, this is your 1, it is only x plus c1. You can choose c as c1 or c2. You can write y is equal to c1 plus cx e raised power alpha x. I take this part to this side. So this is the solution. These are different constants, c1 and some constant c. I can replace c by c2, no problem. So in repeated case, thus when roots are repeated, alpha, so part of solution, actually it is the part of solution, is given by y is equal to c1 plus c2x e raised power alpha x, because alpha were repeated. So what is complete solution? Complete solution is y is equal to c1 plus c2x e raised power alpha x, then c3 e raised power alpha 3x, so on, plus cn e raised power alpha nx. Now you have come to know the solution. When now constants have not got disturbed, you have n linearly independent constants. You have here n linearly independent. You see, it is c1, then c2. It is not getting merged into one constant as previously it was. So it is c1, c2, c3, c4. And now, if you have if 3 roots are repeated, in that case, say you have solution alpha, 3 repeated, then you have another root, suppose it is alpha 4, alpha 5, alpha n. These three are here same repeated. How you write the solution? You write in this case solution, you see solution is y is equal to c1 then plus c2x plus c3, 3 constants you have introduced, x square, you will see you will get x square here, then plus 3 constants are here, c4 e raised power alpha 4x plus c5 e raised power alpha 5x plus so on to cn e raised power alpha nx. Clear? I hope you have got that. Yes. Now if you have all roots, if or roots are, say m roots are repeated, say you have roots alpha, then alpha m plus 1, alpha m plus 2, alpha n. These are roots. Before m plus 1 we have these roots repeated, m times they are repeated. First we took when 2 times we have repeated roots, 3 times we have repeated, now we have m times repeated roots. How we proceed in the solution? Then solution is just look, y is equal to again c1 then plus c2x then plus c3 x square. You see what is the relation between this constant and the power here? It is c2 here, it is 1 less 2 minus 1. It is c3, it is 1 less 3 minus. Then you have c4 x cube. What will be for m? cm x raised to power m minus 1. Here c1, what is power of x? X raised to power 0. c2, what is power of x? It is 1, that means this 2 minus 1. It is 3, this x square means 3 minus 1. It is c4 x cube means 4 minus 1. It is cm, mth constant, so naturally it will be x raised power m minus 1. So what about after this? After this roots are alpha m plus 1, alpha m plus 2, so on to alpha n. Then you have this c m plus 1 e raised to power. Yes, you have one more thing we have forgotten here. I am sorry, this is a very important mistake that we did here. You have e raised power alpha s, I have not written this here. It is e raised power alpha x, very important thing. you have to write this, then e raised power alpha x. Look here, similarly here you have here e raised power alpha x, otherwise we are missing the repeating root here. It is existence is e raised power alpha x. If you have alpha 3 3 3 3 3, say 3 times, then it is e raised power 3x here. So you have to write c1 plus c2x plus c3x square, c4x cube, cm x raised power m. Outside the bracket you write e raised power alpha x, then cm plus 1 e raised to power this alpha m plus 1x plus c m plus 2 e raised power alpha m plus 2x, then so on to plus cn e raised power alpha nx. Well, dear students, this we have completed. Now I think you will be having no doubt you will remember the later on the working rule, but I am just giving you the proof of the working rule. No doubt this will not form the part of your examination. This is a rare case when it forms the part of your examination, but you have to read it, remember this. Otherwise you had to remember the this methods orally, but I am not supporting you to remember the methods orally. I am giving the proof of the working rule. However, because when roots are repeated, we will write the solution this way. If 2 times is repeated, then this solution. If 3 times is repeated, then this. If it is m times repeated, then this. Now last thing that I want to share with you will be when the auxiliary equation has sometimes complex roots, and note that complex root will not be a single one, because we have a fundamental theorem that complex roots occur in conjugate pairs. If the equation has one root alpha plus iota beta, it is necessarily it will have second root alpha minus iota beta. If one root is alpha plus iota beta, second will be alpha minus iota beta. And in that case, how we write the solution of this equation, if it has some complex roots, that will be the last part, and then we will directly go to the solution. Now solution will be very simple. You will solve this equation is now very quickly. For this, when right side is 0, and for another part when right side is x will take different forms. Then we have for the different ways to find out the particular integral. Hope you will follow this lecture, you will revise this, and till then you will wait for the next lecture. Thank you very much.